Hey everybody, Dr. Powers here. We're going to be looking at some examples that are similar to the challenge activities you'll see in Module 8. So anyway, we're going to be looking at two-sample inference, both inference on the population mean and inference on the population proportion. To be clear, it's looking at either sometimes like the difference of population means or the difference of two population proportions, or we'll be looking first actually at another type, which is these paired t-tests. So this is a situation where we're actually looking at a single variable and we're measuring before and after some sort of treatment usually, or maybe we might have individuals who are linked with each other in some meaningful way, like their spouses, for example, and we would be recording the same variable for both individuals. We're interested in actually the average difference, and so here's an example of that type of thing. All right, we wish to test the following claim, which we'll be calling the alternative hypothesis (HA) at a significance level of 0.005. This is a little bit smaller than usual. For the context of this problem, the mu d, the mean difference, is defined as the mean of population 2 minus the mean of population 1. In other words, like it's the average post-test grade minus the average pre-test grade. So this is the average change in grade. Now, make this distinction because in fact we're not looking at the average of the average difference is not the same as the difference of two averages as far as like the distribution of the sampling distribution goes. So this is why a paired t-test is different than an independent sample t-test. We'll get into that in just a little bit. All right, so let's look at this. We believe the population difference scores is normally distributed, therefore a small sample should allow for us to use a t-distribution, right? But we do not know the standard deviation, again, so we must use a t-distribution to model the difference, or I should say to model our test statistic, right? And so here's our sample data. So we have, what do we have here? We've got 9 individuals who take a pre-test and a post-test. So what we want to do actually is look at the difference. I'll make another column here, the difference, and the difference is going to be calculated as the post-test grade minus the pre-test grade. I'm going to take that formula and copy it down the whole way. Now, we're actually going to be doing a one sample t-test on these differences. So we need to calculate the mean of these differences. We need the standard deviation of the differences, so stdev.s, sample standard deviation. And and of course the sample size. And the sample size is we're going to count how many there are. Of course, I already did that, and I got 9. So our null hypothesis is that the mean of differences, this is the notation I'm going to use in Excel, is equal to 0. And what are we saying? We want to see whether the... Okay, so to be very clear, we want to test whether the students on average improve after taking some training class. In other words, we want to test whether the average change is positive. So in terms of our hypothesis test, we're going to write that as the alternative is that the mean difference is greater than 0. Okay, so we're going to have to calculate a test statistic, which is going to be the average change in our sample, so x bar, minus the average change from our null hypothesis, which would be 0, a null change, and we divide that by the standard deviation, divide over the square root of the sample size. This is our t statistic. It's very, very big, and we're doing an upper tailed test. So our p-value is going to be calculated t.dist .rt. I'm doing a right-tailed, and I'll select this value, and I set the degrees of freedom to be 9 minus 1. This is, as you know, it's going to be very, 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 very small. Okay, great. So there's actually a couple ways another way we can do this test, which is with the data itself, we can actually calculate t.test. There's a function in Excel, returns probability associated with a student's t-test. I'm going to give it the two arrays. I'm going to start with the post-test data, and then I'm going to give it the pre-test numbers. And then the question is whether I want to do a one-tailed or two-tailed. I'm going to do one-tailed, and so comma 1, and then I'm going to do 1 for paired. Now this is probably going to give me the lower tail probability, so I'm going to have to take the complement. Oh no, it gave me the upper tail. It knew exactly what to do. Yeah, so this is a way you can calculate that p-value if you want to use the t.test formula. So here it is again, just so you can see it very clearly. This was put in. I did my after, my before, and then I did my a 1 for a one-tailed test, and then 1 chose paired for my type of test. I'm not sure if I'm a little bit iffy about this because I'm not sure if it's calculating array 1 minus array 2, in which case it would have been giving me the lower tail probability for the p-value, but anyway, it's a little bit clouded. It's not very well documented right here, so if you want to be sure, you can just calculate p-value, and you want it to, it should make sense. If my average is at any rate, with a p-value this low, we would say that there is very strong evidence in support of the alternative hypothesis. So we reject the null hypothesis because the p-value is less than 0.005, which recall was our significance level. There is extremely strong evidence that this class improves the test score on average. All right, now here I have the summary statistics for this new scenario. I don't have the data, but that's okay. We can do a test with the summary statistics. So let's see this fuel efficiency of manual and automatic cars. All right, so the table provides summary statistics on highway fuel economy of cars manufactured in 2012. We're going to use these statistics and calculate a 98% confidence interval for the difference between the average highway mileage of manual and automatic cars, and we'll interpret this interval in the context of the data. All right, so what we need to do is calculate a margin of error for such a scenario, right? So we're looking at the mean. Actually, let's do two things. We'll do the confidence interval, and then we'll actually see what this would be in the context of a hypothesis test. All right. So first off, our confidence interval is going to be, let's see, x bar A minus x bar B. The difference in the sample means is going to be the middle of our confidence interval. So I'm going to take the automatic minus manual averages. But then to calculate the standard deviation for this to get to the standard error, we actually have to use some formulas. This is a little bit hairy, so I'll brace yourselves. The standard error is going to be based on let's see, I have to calculate All right, so I need to have var1 and var2. Actually, let's call them var A and var B. The variance for the highway, variance for the manual. Variance is going to be calculated by taking the standard deviation and squaring it. Okay, that's easy enough. I need this is going to be part of the formula, so I'm going to work with the variance instead of the standard deviation. The standard error, I'll just calculate that here. Okay, so standard error is calculated as the it's going to be the square root of the variance of group A divided by the size of group A plus the variance of group B divided by the size of group B. That's the standard error for the difference of means. And then we need to find the critical t-value. This is where things are a little tricky because I need to the degrees of freedom is coming from this formula. The degrees of freedom formula goes like this. All right. So so here is the formula that we have to use for the degrees of freedom. This is when we're not pooling the standard deviations. This is the typical formula. Unless you know for a fact, or you have very strong evidence that the variances of the two populations is the exact same, you should use unpooled variances. So we take the standard error that we just calculated, and we take that to the fourth power. And we divide that by a sum of two things. The first is the variance for group A divided by the size of group A, and that's going to be squared divided by this n minus 1, the size of group A minus 1, plus I'm going to do the exact same thing for group B. I take the variance divided by the size. I'm going to square that. I'm going to divide that by the size minus 1. Okay, look at that. My degrees of freedom, 49.85. That's the degrees of freedom for the t distribution that we'll be using. So we need to find our critical t value, and this is for a 98% confidence interval. So that's going to be t dot inv. Oop, I have to put equals t dot inv. I'll do dot 2t, and I'm going to put in 0.02, and the degrees of freedom is this number I just calculated here, 2.4048. Okay, so my confidence interval lower bound is going to be the difference of these minus the standard error times the critical t-value. That's the margin of error that those two things multiplied give me the margin of error. The confidence interval upper bound is going to be the difference of these plus the standard error times the critical t. And there you go. So that's how you calculate a confidence interval in Excel for a two-sample t-test using the unpooled variances. The degrees of freedom is that's the messiest thing to calculate of all. Once you have the degrees of freedom and the standard error, you can actually calculate, right? You can use Now let's talk about the hypothesis test. The null hypothesis test is that mu1 equals mu2, or I'll call it A and B. Mu A equals mu B. And let's calculate an alternative hypothesis that the two groups, the two populations, automatic and manual, do not have the same mean. So mu A, I'll use this notation, does not equal mu B. This is very sloppy notation because Excel, I don't have the not equal sign handy on the keyboard, but you get the gist of it, hopefully. Now, I'm going to calculate a t-statistic, right? That's going to be the difference, it's x bar A minus x bar B minus the difference from the null hypothesis, which is 0, right? Because in our null hypothesis, I'm saying that the two means are exactly the same. In other words, mu A minus mu B equals 0 in the null hypothesis. And I'm going to divide that by the standard error that I calculated. That's my t statistic. And then I'm going to calculate a two-tailed p-value. It's going to be t dot dist dot r dot 2t. Oops. And I'm going to give it my value and my degrees of freedom, which is calculated over here. And oops. You know what? I think it doesn't. The two-tailed test doesn't like negative t-value, so I'm going to have to put in the absolute value. I'm going to put in the absolute value of this negative test statistic. Yeah, that looks right. 0.00109, meaning that there is strong evidence that the means are different for highway and for automatic and manual cars. So again, this is that I had to do because I had a negative t-value or t-statistic. I took the absolute value of that when using the t.dist.2t function in Excel. All right, this is messy stuff. There is a t.test function in Excel, but it takes arrays. It's not going to take the sample statistics, so we can't use it for this kind of a thing, unfortunately. So this is the best I can do. I'm calculating this stuff. Excel is not built for this, so there's definitely easier ways to do this kind of a test, but this is how you do it in Excel. Okay. All right, let's look at this. Researchers studying the link between prenatal vitamin use and autism surveyed the mothers of a random sample of children aged 24 to 60 months with autism and conducted another separate random sample for children with typical development. The table below shows the number of mothers in each group who did and did not use prenatal vitamins during the 3 months before pregnancy. So we want to determine whether there is significant evidence from here that the proportion of babies who develop autism differs between these two populations, women who take the vitamins and women who don't take the vitamins. Okay, so the null hypothesis is that P V that's the I'll do NV equals PV. Right, that's the proportion for mothers who we're talking about the proportion of the children who develop autism. That the proportion's the same for the two populations, and then the alternative hypothesis. Oh, that's formatted funny. P and V. We're going to test whether, let's see, what is this saying? They're studying the link between prenatal vitamin use and autism. It's not clearly stated here that I think that certainly the reasonable kind of assumption to be, or a reasonable claim to be tested here is that that the risk for autism is decreased when taking vitamin supplements. If that was the claim that was being tested, in fact, I'm going to clearly state that. Okay, if we're going to test whether prenatal vitamins are linked to a decreased likelihood of autism, the alternative hypothesis is going to be P no vitamin is greater than PV, right? The proportion for those who do not take vitamins is greater. We're going to have to calculate a few statistics here, so we need to find, this is going to be so messy looking, P hat NV minus P, I'll just calculate the two P hats. P hat V, okay, so the proportion, sample proportion for the non-vitamin is going to be 11 out of the 181. The proportion for those who had vitamins was the 143 out of the 302. And I'm going to have to put in, you know what, I'm going to reorganize this a little bit. I'll just put them in columns. So I have my not vitamin and my vitamin columns. And so I need to have the sample size. I'm going to put those here. We have 181 and we have 302. Then we have to calculate the... Okay, so then we look at the pooled p hat, which is going to be it's not column specific, but it's the total. Actually, it's right there, 254 divided by the 483. Well, let me do it like using this. It's the total who developed autism over the total who were in the sample. And now the null hypothesis is really that both populations have the same proportion, and so we're going to use this pooled p-hat in our calculations of the test statistic because the null hypothesis kind of assumes that both of these samples are really coming from the exact same population. So the z statistic is going to be calculated as you take the difference in the two proportions. So this, the non-vitamin minus vitamin, that's the numerator. Or actually, it's going to be this minus 0 because in the null hypothesis, I'm assuming that the difference is 0 of these two proportions. Okay, then the denominator is going to be the square root of, I'm going to calculate, it's similar to the standard error for, actually, let's just calculate the difference. P hat NV minus P hat V. Let's just do these in pieces. This minus that. Okay, I'm going to calculate my my standard error. This is going to be the square root of, I take my pooled proportion times 1 minus the pooled proportion, and I multiply this by 1 over n1 plus 1 over n2. And all that's square rooted. Now to find my z-stat, it's going to be the difference in the two sample proportions minus 0, because in the null hypothesis I'm assuming that the difference is 0, that the two proportions are the same, the two population proportions are the same, and I'm going to divide by that standard error. Okay, well, this is certainly a large z-statistic, and we know that to calculate the p-value, we're going to calculate a right tail. So I'm going to do, well, to do the right tail probability, it's going to be 1 minus norm dot dist. I'm going to give it this value, give it the mean of 0 and the standard deviation of 1, because I'm finding the standard normal probability out in the tail, and I'm going to use true. Remember, I'm doing 1 minus because this function gives me the left tail probability. If I want the right tail probability, because it's a right tail test, I need to use this 1 minus. That's the complement. And I get a very, very small p-value, as I expected I would. Well, okay, so what do we do now? So with all of this, we get a p-value that's very, very small, and I would make a conclusion. I would say there is, so we reject the null hypothesis. It's less than 0.05. We didn't specify the significance level, but it's less than any significance level we would have considered, certainly. I mean, we would have to be very, very strict to use 0.001 as a significance level. But yeah, any kind of typical significance level, we're definitely below that threshold with a very small p-value. So there's strong evidence that taking prenatal vitamins is linked to a lower proportion of autism. I'm being careful with my wording. I don't want to claim that it's the cause. Certainly, one would think so from this, but you have to remember that there could be other variables at play. This wasn't. I imagine. It doesn't say that this was a controlled experiment where the mothers were forced to take or not take prenatal vitamins. This is the kind of thing that you would observe after the fact. You would survey them and find out, did you take prenatal vitamins, right? And so anyway, there could be many other factors at play, and but there is some sort of relationship here. So there is a dependency, but I'm not saying that there's a causal relationship. So I hope these examples are going to be helpful for you in going through the challenge activities. I know that in Zybooks, you don't actually have to calculate any of these statistics. You just have to understand them and interpret them. So the work you do is going to be a lot simpler than this. You're not going to have to use all these formulas in Excel to do the work. But it's helpful to know kind of where the numbers come from. They'll make a little bit more sense when you're seeing them. All right, well, I will sign off now, and I hope that you have a... I made a typo here. It's vitamins, not vitamins. Hope you have a good one. Bye.